Hello everyone, I am Raunak and I'm here to talk about our research today. I will be presenting PhobosBC, which is a blockchain-based system for crowd sensing after natural disasters. This is the outline of my talk. I will introduce the reason for our research, then our initial assumptions and research objectives. I'll discuss some research that has inspired our system. I'll introduce the components, agents, and operation procedure for PhobosBC. And finally, I'll talk about the agent-based model we created to evaluate our system and the results we obtained. In the immediate aftermath of a natural disaster, there's an initial rush of inaccurate and often inconsistent information. To deal with it, there is a need to quickly create a first-order approximation of the ground details. The most logical source of this information are the affected people themselves via crowd sensing. Crowd sensing on its own has some inherent challenges. Collating multiple types of data and keeping them from organized and referenced is difficult. Erroneous data caused by malfunctioning sensors or untrustworthy actors can contribute to lowering the accuracy of this information. And as the size of this collected data set increases, maintaining integrity becomes a challenge. We attempt to solve all of these problems through the blockchain protocol in PhobosBC. An example disaster scenario where PhobosBC would be useful is a major hurricane striking a city in the Gulf of Mexico, which might bring gale force winds, localized flooding, life-threatening storm surges, and other general flooding due to levee breaks. The immediate need in such a situation is to locate paths of access to wrecked areas and then locating downed utilities, after which first responders need to find destroyed homes and shelters and begin rescue operations. The initial assumptions under which our system is designed to operate involve massive disruptions to existing communication networks, damages to area infrastructure creating obstructions to movement and thus rendering existing maps functionally useless, and finally, we assume that common people have the access to some manner of communication device, such as cell phones, that have the capability of at least limited local transmission and reception. The research objectives for PhobosBC were robustness. The system must degrade gracefully and be able to appropriately handle missing or corrupted data. Collaborative problem solving. The system must be capable of scalable and distributed problem solving using several volunteers pooling their resources. Decentralization. We can safely assume that there are no central authorities that we can reliably trust once a disaster has occurred. Thus, we should have some mechanism to handle dispute resolution through consensus mechanisms. Our system was inspired by various published works. Bhattacharya et al. And Kuchuk et al. Proposed a crowd sensing system for disaster scenarios that did not assume complete decentralization and required at least multiple local authorities. While Yuan et al., Ming et al., and Yang et al. Proposed blockchain-based crowd sensing systems, but they rely on existing infrastructure and access to some powerful computational capabilities to run the blockchain. They also require mining for task assignment, and thus they are fairly energy inefficient. We compared the existing solutions with our assumptions and objectives, and we found that none of them cover all of our requirements, and thus we developed PhobosBC. Our solution to our initial assumptions and objectives is PhobosBC. PhobosBC is a system which combines the knowledge of certified workers or volunteers to automatically generate a working digital map of accessible areas within the disaster-affected region. PhobosBC aims to generate a complete and correct graph of accessible paths through a disaster-affected region through data collected by volunteers equipped with some form of IoT-enabled device, such as a cell phone. Each node of this graph is a point submitted by a data collector. When this collector submits their point, a data processor runs a smart contract to check whether the created route is valid and adds it to the chain if so. Anyone can query the blockchain and receive the latest compiled map. There are two major components of the PhobosBC system. First is the data summarization system based on the Bhattacharya et al. Paper. It is a fundamental model run by every data processor in the system. It creates pedestrian maps from trajectory traces acquired by the collectors. It is designed to be energy efficient and fault tolerant. The second system is a trace management system. It is responsible for periodic collection of trajectory points through GPS receivers present in each volunteer node and creation of trajectory traces from such points. We have thresholds between successive collections to prevent oversampling. There are two major agents of PhobosBC. First, the data collectors. They are individual people who continuously collect their current GPS location. A trace is created every time the distance between collected nodes exceeds a fixed thresholding distance. This trace is sent to the data processor. Data processors are fewer in number than collectors, and they are pre-assigned based on computational capabilities. They submit the data collected by the collectors to the blockchain through a smart contract and then performs truth discovery. They also merge their local ledger with the global ledger and can view all the collected data stored in the blockchain and thus infer a constructed map. This is how PhobosBC operates. First, the data collector collects a trace and broadcasts to all local nodes that are within range. It then waits for confirmation of delivery and successful integration from at least one processor. Until confirmation, all subsequent traces are held in a queue. This process then repeats until the data collector voluntarily stops or the trace management system detects errors and disables the data collector. Next, the data processor starts package verification, author identification, trace processing, and result provisioning. This is an overall look at how PhobosBC is deployed within a real-world geographical area. The PhobosBC system workflow can be seen in the figure on the right. First, all collectors and processors will need to register with the blockchain system during initialization. Next is an automated process where once registration is complete, all collectors receive their starting points. Next, the workers upload any sensory data to the blockchain. It is then validated and qualified data is accepted and recorded, and corresponding workers are made known. To ensure the correctness of maps, the smart contract then runs a truth discovery process. The processor downloads all information related to the maps from the global map and posts all the information to their private blockchain network. If the current state of the blockchain is satisfactory, any requester automatically gets a copy of the current product. And finally, each processor constantly runs an integrity check on the blockchain data, and all entry into the blockchain is frozen if a majority of the collectors find error in the data. In order to assess how PhobosBC would perform in a real-world setting, we designed an agent-based model to simulate a very specific disaster scenario. For the purposes of the simulation, each volunteer would be an agent in this system. We implement data processors and data collectors as agents, exploring a graph with the same layout as the roads of a city. These agents have the capacity to communicate with each other and run the smart contract. We built two different simulation models, one for PhobosBC and one which assumes centralized control. The system, whose structure can be seen in this figure, has several controllable parameters. These parameters are the number of agents, the total number of time steps per run, the failure rate, and the number of points collected by a data collector in a single simulation step. A single simulation step represents the movement of an agent from one node to the next. We simulate the performance of PhobosBC to determine the effectiveness and accuracy compared to an idealized centralized system. The experiments were performed on a local computer running Windows 10 with an Intel i9 processor, 32 gigs of RAM, and an NVMe drive with 8.0 gigatransfers per second. The simulation was performed using the agent-based modeling library Mesa, which is written in Python. The smart contracts were written in Solidity, and they were tested using Ganache, running the Ethereum blockchain. For ground truth, we utilized the Harvey Damage Assessment GIS dataset from the city of Houston. For our base layer, we used a city road network map from OpenStreetMaps through OSMNX. Using flood damage reports, we generate non-passable roads in these road networks. The city model is a road network graph imported from OpenStreetMaps simulating a section of Houston. The graph is stored as a NetworkX object, where roads are edges and intersections are vertices. The vertices stores information, a reference ID, location information in latitude, longitude, and height of maximum water inundation level. Our generated map is then compared against this flooded city road network map using the evaluation procedure, which we will describe next. For our evaluation procedure, rather than comparing edges, we check whether each path in the original map has a corresponding connected sequence of edges in the reconstructed map. The percentage of paths in the ground truth map which were found in the reconstructed map is used as our evaluation metric. For comparison, we generate an idealized, centralized model. In this case, there is just one data processor, and that agent is available to receive data from every data collector on the field. Similar to the standard model, the central data processor has a 2% chance of going down at any point. In order to simulate the irregular availability of a central point, we give it a 25% chance of coming back up after every 3 time steps. We evaluate this setup against our standard setup and compare how long it takes to reconstruct 95% of the ground truth map. The results can be seen here in this figure. We can see that PhobosBC performs consistently better than the centralized model over various agent numbers. We can also see that PhobosBC is also capable of reaching fairly high accuracy levels relatively quickly using very few agents. For this baseline comparison, we limit the number of time steps to 350 for both models and then vary the number of agents from 50 to 1000. The results of this experiment are shown here. It is clear that although both models have poor accuracy with low agent numbers initially, PhobosBC is quickly able to reconstruct a large portion of the map. Using PhobosBC, roughly 500 agents are capable of accurately recreating the ground truth in 350 time steps, making it faster than the centralized approach by an average of 50 time steps. We observe that PhobosBC can maintain its performance far longer than the centralized approach. We can see that the system is able to tolerate up to 35% to 40% node failure. However, when approaching 50% failure rate, the system is unable to maintain a high reconstruction rate. The centralized model performs far worse as the central node going down irrevocably handicaps the entire system. Even a 20% node failure rate decreases its map reconstruction rate to below 60%. To test an extreme case, we run a simulation with 1000 agents at 1000 time steps. The reconstruction rate for PhobosBC stabilizes at 59%, while the centralized model stabilizes at 20%. This is slightly higher than the performance at time steps of 350. This indicates that simply letting the system run for long periods of time does not lead to a better map for high failure rates. Finally, in conclusion, we present here a framework for crowdsourced map building using a blockchain-based system following a natural disaster. The proposed system relies on a blockchain to provide robustness and decentralization and the ability for multiple disparate users to contribute their effort. The system is designed to handle disruptions to communication networks and infrastructure, requiring the end user to only have a simple mobile phone. We aim to further introduce more advanced blockchain capabilities into the system in the future, such as complete confidentiality of users and more robust resource management. We also aim to introduce an incentive mechanism within the system to reward volunteers for delivering better and more accurate reports. Thank you.